Hello everyone and welcome to this very short video where we're going to work together the solution for this in-class problem where we are asked to demonstrate that the following compound proposition is always true. We are going to do that by building a truth table, but before we do that, I invite you to take a moment to analyze what we have here in this seemingly complicated notation. What we have here basically is a compound statement that says something like, if we have only three events, A, B, and C, and we know that all of them are mutually exclusive, so only one of them can be true at the same time. This is what the SOR means. There's only three possible events, and it has to be only one of these three. And we have observed that A is not there and B is not there, so we have already discarded these two events. Then that only leaves us with the third statement, C, here. So if there are three possibilities and I discard two of them, then by default, the third one has to be the correct one or the truth one. So how do we do this? Well, so we know that we start by writing our atomic propositions, and those are A, B, and C. And then we start by building up the number of rows that we are going to need. So we know that we have three atomic propositions. So we're going to have 2 to the 3. That is going to be 2 times 2 is 4, times 2 is 8. So we're going to have 8 rows here. Excellent. So we're going to start by filling up our values. So we're going to start by having 4 times T, 4 times F, then 2 times T, 2 times F, and T, F, T, F. And that way we have established all the possible combinations. You can think of it as some form of decision tree. So we have an event A that can only be true or false. We have an event B that can all be true or false for each of these two scenarios, right? And we have an event C that also for each of these events, or sorry, each of these routes here can be either true or false. So we end up with 1, 2, 3, 4, 5, 6, 7, 8, which are exactly the same combinations we have here. And here you can see that we have pretty much just written down all these different paths. So that's what we have here and here and here and so forth. But anyway, so we have here our atomic propositions, and now we are going to build in our first operator here. So this is the SOR operator, right? So we're going to have here, for simplicity, I'm only going to write here the SOR, and now we start filling this in. So we know that SOR is only true when only one of these three events, or sorry, only one of these three atomic propositions is true. So here we know that it's false because all of them are true. Here it's false because we have at least two that are true at the same time. False because we have two that are true at the same time. Here we have that it is true because only A is true. Again, false because we have two truths. True because only B is true. Sorry, there is a light. True because only C is true. And then here we have it false because none of them is true. So now we have here not A and not B, right? Those are the next elements that we have here on our whole compound propositions. I'm going to do here not A, not B. And we're going to see here that pretty much not A ignores totally the values of B and C. I'm only going to be taking into account the values of A. So I'm going to do not A is going to be false in the first 4 cases, right? Because those are the cases where A is true, and that is not what that is exactly what not A means. And not A is going to be true when A is false, right? Because exactly that is what not A means. Now, similarly for not B, we're going to only do it in terms of the truth value for the B atomic proposition. So here we're going to have false, false, true, true, false, false, true, true. Then we have here, what other operation we have? Well, we have here an AND that is going to link these two together. So we're going to have this AND here. We denote it with a parenthesis to indicate that it's the AND that appears here within the parentheses, right? So here we have 2 parentheses. And now for this one, I'm only going to take into account these 2 columns. So when is both not A and not B true? So we have it here that in here, not B is true, but not A is false. So that is not the case. We keep moving forward. We have the opposite scenario here. And only here at the very end, we have 2 instances where both not A and not B are true. So we do that 3 true. And all the others have to be false by default. Oh, I am doing it a little It's getting a little crooked, but okay, I hope this clarifies the point. Then we are going to have this AND that I have here. So this AND denotes the cases where this SOR here is true and this AND here is true. So this is the outer AND that I'm going to have there. And now I can do it such that I'm going to just take a look at these two columns. I'm going to ignore all the other values. Just take a look at this column, the big SOR, and the AND within parentheses, right? So I am trying now to figure out this AND here. That's what I have here. Let me actually delete this or erase this. So now this is the one that I am working on. And this is only false when this is true and this is true at the same time. So we have only one true value here, only one instance in which when this is true, this is also true. And now we're going to fill in the implication. Oops, sorry guys, coming back from some technical difficulties. We are now dealing with the last step here, which is the big implication that we are going to be testing. So we have already tested all the operations before, along with the atomic propositions. Now we are yet to test the most important part, which is the implication here. So whether when all of this is true, then it is also the case that C is true. Or whether, yes, whether if this happens as a condition, whether that results on C being true. So that is what the implication here is telling us. So remember that on the first set of materials, we discussed a couple of propositional arguments that are always valid. So we talked about modus ponens, in which we have if A, then B, and then I observe B, and then I observe A, then B. This is always valid, right? So this is always valid. It makes a lot of sense. If I have established that there is a condition that results in a consequence, and I observe that same condition, therefore I should expect to also observe the consequence. That is the modus ponens. We talked very briefly also about the modus tollens, in which we have a similar scenario. If A, then B, and not B, therefore not A. This is also, again, always valid, and it makes sense, right? If I establish that there is a condition with its corresponding consequence, and the consequence is not there, then that must mean that the condition should not be satisfied. So this is, again, modus tollens, always truth. But remember that we also had some other forms of fallacy. So we talked about affirming the consequence. We talked about this propositional argument as something that is not always true. So we said that if we establish that if A, then B, and we observe B, it is incorrect or is not, it would be incorrect to necessarily assume that A has to be truth, right? So think of it that this is a condition that causes B, and we observe the final result. It would be incorrect to assume that this specific condition was met. We had a similar fallacy that is called denying the antecedent, in which if we say if A, then B, and then I observe not A, therefore not B. Again, it's a similar logic. If I have established that there is a condition that results in a consequence, and I don't observe the condition, therefore the consequence is not there, this would be an invalid reasoning. It's not necessarily truth. We can think of it as there might be other possible conditions that result on there might be other possible competing conditions other than A that can result on B. So it's a little bit like that. I can tell you, if you do 100, if you get 100% on all your quizzes, you will get an A+ in this class. That is true. But it is not true that if you don't get 100% on your quizzes, you are now doomed to not get an A+, because you do have the extra credit assignment. So that is a great example for this fallacy. All that to say that when we test this implication here, well, in doing that, now we know that we can only do it we can only really assess whether this is true or not by taking a look at the cases where this whole first bit of the compound proposition here is true. So really, we can only test it here when this is true, and we have to test whether it is actually the case that C is also true. So we go here true and true. So as far as this case shows, this whole implication is true. And for the remaining of instances, again, similar to what we would do, or similar from what we learned from denying the antecedent, really denying that this happens should not be conclusive as to whether or not C is true or not. So for all these cases, we are going to default to true. And that is what we have here. So we have shown here in doing all this truth table that this little statement here is always truth.